if we just considering n-1 dimensional foliation, this is another definition that we can take of foliation. But there, I'm assuming that the one form should be integrable. It's not always the case. We just take any non-vanishing one form. It won't correspond us to foliation. But if, as a special case, if manifold dimension is 2, then one dimension and 4-dimensional one position are the same thing. It's just one. In that case, all 4 definitions are equal. So these 4 are same. We can go from one to another. In fact, if you look at in the coordinates, if we have a vector field del by del x plus del by del y, if this corresponds to a position, we can find a corresponding one form, which is f dy minus g dx, which will give us the same foliation.
Sorry, please carry on. I'm so sorry.
Now, here, if the dimension, because I get this is an exercise, if the manifold dimension is 2, then we don't need to put the integrability condition on one form, because that's automatically there. So, what's the integrability condition? It was that it should be identically 0. Omega match T omega. And this is now a holomorphic 3 form on a complex 2 dimensional manifold. So, this is automatically 0. So, holomorphic foliation. Now, why I'm writing these definitions? This is because now I want to move on to singular holomorphic foliations, and to do that, I can't just start with something like this as it is, because in general, like what a singular foliation is, a classical definition is just that it's a partition of the manifold into different dimensional leaves. So until now we have assumed that there are no singularities. So all the leaves that we were thinking, they had the same dimension, same dimensional submanifolds. Now if we assume or if we allow singularities, the objects could have different singularities, different dimensions. For example, if we look at this, so the definition of a singular holomorphic foliation, or just a singular foliation, tells you that even this point is a leaf. Although near this point, our object does not look like the stacked thing. So these are what we call as the singular points, where our foliation does not look like that stacked objects. Now, we don't want this singular set to be anything. We want some control on this singular set. Some control in the sense we want some objects to define this singular set. That's why we will define singular foliation with respect to some like this perspective. So what we do is we consider this definition. Now, what this definition says that holomorphic foliation is locally given by non-vanishing holomorphic vector fields. What we just change is that now we'll remove the non-vanishing part. We consider an open cover of the manifold and we fix holomorphic vector fields. Now we just want them to be non-zero, not non-vanishing. They can vanish at some point. And yeah, and the foliation would be the leaves or the integral curves solving this differential equation or these vector fields. And the singular set would be the zero set of these new vector fields. Okay. Yeah, why do we want to consider this definition? So remember when I started giving some motivation of holomorphic foliation, the first thing or the only thing that I started with is that the classical motivation was to study differential equations, holomorphic differential equations, and most of the time they do possess some singularities. we were considering polynomial differential equations y by dx as xy and xy to study this differential equation. They do possess singularities. So of course we want to study this singular holomorphic foliation, as in like the right candidate would be vector fields, because these are given by solution of vector fields. But after some time we'll see that we can just give we can just call our foliation to be singular foliation by considering some analytic set of a manifold M be a small set, and we say a singular foliation is just a regular foliation or holomorphic foliation outside this set. So this is more natural, right? If we think about it, what we are saying is that there is a small set outside which we have an actual foliation, and we'll see that this definition, if we go through this one, they both will come to be same. Just having this information, we can get these objects locally, these vector fields. Yeah, another set of motivation is that holomorphic foliation not always exists on complex manifolds. So if we just think about complex projective spaces, CPN, on CPN there are no foliation without singularities. All foliations are with singularities. So of course we want to study these objects. And yeah, so we can do this singular study for, of course, for dimension 1 and 4 dimension. I'll just focus on dimension 1. The 4 dimension 1 study would be just similar, just minus 1. Let me so singular foliation of dimension 1 on a complex manifold M is defined by this collection X and G's that this Xi is non-zero holomorphic vector field. Holomorphic vector field for UI. So I'm replacing non-vanishing with non-zero. Just to, these are different. Non-vanishing means it cannot vanish at any point. Non-zero means it's non-zero at some point. So that's the. And these GIJs are again non-zero holomorphic maps or functions in the intersection which relates these objects psi Gij times x. This is a singular holomorphic foliation, and in this case, before I define the singular set, look on UI. On UI, we call the singular set of the vector field xi as the zero set. That's right. Points where the vector field vanish in the open set UI. And of course, this singular set of this set is an analytic set, because this is given by xi is a holomorphic vector field, so it has these components f1, f2, fn, and these are the holomorphic maps which are defined in this set. So it's an analytic set, nice analytic set, and we have this on each open set. We have this analytic set on each UI. Now on dimension uj, if it is non-empty, if you look at this condition says that these two objects on the intersection coincide, because this is a non-zero holomorphic function. If xj is 0 at some point, then xi is 0 as well. So these local analytic sets they patch up and we get a
Sorry, xi is 0.
Yeah.
Xj need not be 0, right? Because gij could be 0.
no, but then I have gji.
Ah, you have it for all.
Yeah, I have. So what we get is we get on the complex manifold this global object. Let's call this as singular set of the foliation. We denote it by this. This is restricted to ui. This is just this set is called as the singular set of F. Now what a singular holomorphic foliation is and what the singular set looks like. As an example, as I said, we can just take on C2 any non-zero holomorphic vector field and we can solve this to get a singular holomorphic foliation. But now comes the important part. We want this set to be small, the singular set of this foliation. We want this set to be small. What's the maximal? What's the depth? What's the dimension of this singular set could be? The highest dimension, maximum dimension of this singular set could be. I'm asking. So, what's the maximum dimension of this singular set? N minus 1, right? We could have this xi. This is a holomorphic xi. If you look at the coordinates, look at this f1, f2, fn. These are defined by this. So if this zero set of this vector field can have dimension n minus 1, and since the vector field is non-zero, that's the maximum dimension that this singular set could have. But what we want is we want something like this. Okay, we don't want it, but we will get it. So this, let me say 4 dimension of singular set of the foliation of this analytic set. So its dimension would be at most n minus 2. How do we reach there? This is what we see next.
So let me ask you one more question.
Yes.
So what is kind of the co-cycle condition or whatever on the gij? So if I wrote xj as gji xi,
yeah,
then but it's not clear that gij gji is 1, right?
Yeah, it will be. Yes.
Because xi could be also vanishing.
Yeah, but the zero set of xi and xj through this definition are same. Okay. Before,
sorry to.
Yeah.
So, but GAGs could have 0.
No, GAGs are holomorphic, non-zero.
No. Okay. Yeah. Sorry. Non-vanishing. Yeah. That is the part.
Yeah, this is non-vanishing. So this is the representation of non-vanishing. Maybe I said non-zero. Sorry.
No.
But this is what I mean.
Thank you.
Sorry, I couldn't. Yeah. So from this definition, what it looks like that this analytic set, this singular set, it can have dimension n minus 1. But we'll see that we can always reduce this singular set to be dimension n minus 2, less than equal to n minus 2. This is what we are going to see next. Before that, definition. So when P
a multiplicative data. It's not representative data. This is in terms of vector fields.
So we call a point in this analytic set a removable singularity. If we can straighten out foliation near P. So what does this mean? This means that we take a point here. So it's a point on manifold. Suppose we can assign this point to a leaf of the foliation, and locally the picture would become like this. Then that's a removable singular point. Let me give you an example how this can happen. So just imagine we are in R2, R2 or C2, and we have this vector, we have this solution, except this point. So, okay, maybe this is not a good idea because of the definition that we started with. Look at the vector field x and y times. So this is a holomorphic vector field on C2, non-zero holomorphic vector field on C2. Now, what are the leaves of this vector field or will look like? So the foliation corresponding to this vector field. This is our x direction and this is our y direction. First of all, we check the singular set. What's the singular set of this foliation? It's where x is 0. So it's this set. This is a singular set of this foliation. And what are the leaves? These are this complex line parallel to x-axis. Now, suppose we take this point on the singular set, we can assign this point to this leaf and all other points to the respective lines, and get foliation on whole of C2. So here in this case, every singular point is a removable singular point. So this can happen. Just by looking at this example, I'm telling you that these things can happen. The singular point could be removable.
Just to state the obvious, in case someone's confused, x and y are both complex.
Yeah. Okay. So okay, let's Z.
No, it's fine. It's fine. I just
Yeah,
want
but I think that this is better. X and Y we use for
to get used to
real
the
and
expectation.
So is this point clear that why a singular point could be removable?
Is it equivalent to finding a non-zero vector field to define the foliation?
Exactly. Non-zero or non-vanishing.
Yeah.
Yeah. I mean, the basic idea of proving all these things would be exactly that. Okay. Yeah. So this is a definition of removable singular point. Now we call F to be saturated if every single set of foliation is non-removable. So I take out all removable singularities, and if a foliation has every singularity non-removable, that is saturated. Saturated in the sense, if there are some removable, I'm assigning those singular points to some leaf, and we get another foliation, and we can keep on doing that by assigning those removable points until we get saturated with respect to this program. What is this? Yeah, so straighten out in the sense that's what I said like this. Because if we assign these points to these leaves, locally we have this. But if our vector field is this, our foliation is this, then we cannot straighten out our foliation in any neighborhood of this point. So this is correspond to Z del y del Z plus W del y del Z. So this is a non-removable singular point. You cannot you can change coordinates like however you want, but we cannot get a local picture like this.
That point is passing to more than one leaf.
Yes, yes. We cannot assign it to just one leaf. Yes. Okay. Yes. So corresponding to every foliation with this definition, there is a unique saturated foliation.
So if point is going to only one leaf, that's the direction of removal or
What?
if a point is going to single leaf,
Yeah.
then we say that as the characterization or
No, actually, I mean,
Not defined.
Just going
No, no,
from
no.
a leaf
So-
in the closure
so
of
something like this will happen.
So
actually.
we have to make sense of it.
Even something more yet can happen. It could even approach the singular point nicely, but still it could be singular. So we have some vectors like x z square del y del z plus w del y. Some vector field like this, or maybe z and w square. So what happens is one of the leaf is this, and all other leaves kind of stays away.
So the leaf itself is singular over here.
Yes. So
Yeah, that's what I.
then you cannot straighten out. So this is a non-removable singular point, although it only kind of corresponds to just one leaf. So these kind of things can happen.
That is Z minus from the
Sorry, what? Say?
plus is minus Z minus Z delta Z minus from the then
Then it's
I'm asking that yeah, if there is a minus then singularity
no, I guess that there is still a singularity because these two objects will still be leaves of this position, and this point belongs to this two. So you take this z and then you take z equal to 0, assign here, the vector field becomes del by del w times something. So this is invariant, and this is also invariant. So you have two different leaves which kind of correspond to the same singular point. So it's still non-removable. Okay. So yeah, what I'm saying at the end is corresponding to a singular foliation, there is a unique saturated foliation. That's by definition because we are just assigning those removable singular points to the leaves. Now, if saturated foliation, saturated singular holomorphic foliation, and then this dimension or codimension of this singular side of this foliation. So what this result says that even if we start with some singular holomorphic foliation, this singular set analytic set has 4 dimension 1 or dimension n-1. We can always saturate, and so it says the n-1 dimension components, the regular part of this, those are always removable singular. Here, what I'm trying to idea that I'm trying to give, that we can we could possibly from this definition have the singular set to be big as in the 4-dimension one, but most of these points, the 4-dimension one components, the singular points on these components are always converging there. This is what we will show.
You still get an analytics.
Yeah, we still get an analytic set, but it's 4-dimensional. It's very small. Let's do this. I'll give you the idea, the process. Consider this manifold M, and here is my analytic set V. Now, the F is saturated, so I want to put some. I want to show that this set is very small. Suppose this 4-dimension singular set of this coordination is 1. Suppose we have components of 4-dimension 1, and let Q be one such component. We take 4-dimension 1 component of the singular set, and let's maybe I don't think a manifold. We take a point P in M, and if P is not in singular point, I can always find a neighborhood around P is away from the singular set itself. The singular set is an analytic set. If I have a point which is not in the singular set, you can always do that. Now, if you look at the definition of a singular holomorphic foliation, we have these holomorphic vector fields which are defining this foliation. So on this vector field, I have the vector x alpha. On the chart Q alpha, I have the vector field x alpha. Now I have to define new set of vector fields, or new set of data, such that corresponding to that data, the singular set is small, and that data is kind of extending this data in the sense of foliation. This is what I have to do. So if I'm away from the singular set, I can define a new vector field to be the same. Okay, and if we take a point in the regular part of the component, then we look at this point and we take this label. So since this is an analytic set, so this U alpha is, let's say, U alpha intersection. What?
Regular points of the analytic set.
So this is a singular point because W is a component of singular set.
So where the dimension of the analytic set is the maximum dimension.
Yes. So, I mean, it's a dimension of the analytic set, which is so since it is an analytic set, locally there exists irreducible analytic set H alpha. So locally, this intersection, this analytic set in this open set is given by some irreducible holomorphic function. And what we can do is we can write our vector field x alpha here, because this vanish on this set. This vanish on this set. We can write this as h alpha power some k of k alpha times another vector field x alpha theta. We take the maximal power of this h alpha from the components. you see x alpha is x alpha 1, x alpha 2. So if this vector field vanish on this set defined by h alpha, then h alpha divides each of these components. So we write this each component as h alpha to the power something times another function which does not vanish on this set, and we take the least common power. So that what happens is now x alpha theta is does not vanish. Does not vanish on here. So,
Here, H alpha is non-vanishing, right?
No.
H alpha is non-vanishing.
the h alpha is vanishing. H alpha is the secondary function.
Of the analytics. On the analytics set, it is vanishing.
I mean, it's an irreducible component. So this set is exactly the zero set. So I mean, by definition, it won't vanish outside the other points other than this, because this is by definition. This is analytic set, and this is the defined function of this analytic set. So okay, so so only two kinds of things happen, right? What I'm trying to do is I'm trying to remove this n minus 1 or 4-dimensional component. So either a point can belong to this set or it cannot. If it does, then I can reduce my vector field and get another vector field. And if it does not, then we take the original vector field. So we get another set of data. Now, what we
I mean, this analytics set might have singularities.
yeah, I'm taking okay the regular parts. So yeah, because I'm taking I'm taking a regular part. Because the singular part of this component we can still assume, because we want this just the restriction of this, that dimension of this set should be n less than equal to n minus 2. So whatever the singular side of the components, they will come into that.
So the C alpha will be small enough that it will not
Yes.
contain any singular piece of the.
Yes, maybe
We can shrink through alpha.
maybe just two, yeah.
But that's not quite right.
No,
because-
actually, so what happens is, although I'm writing just u alphas coming from here,
can-
since I'm working with this point P, I'm actually taking some finer
Exactly,
areas.
shrinking with you alpha.
So these u alphas are not exactly those, but they are much they are finer. It was I didn't want to write that was it will create confusion
Yeah, that's
writing
fine.
between the first one and the point. That's why I just trying to give the idea. Yeah, so we are taking this to be small enough so it won't contain another like singular points or the 4-dimensional
So that
ones.
statement itself is not quite right, and what you had written earlier is better. You alpha and intersect alpha.
Yeah.
But you just mean that there are no singular points in that.
Singular points of the singular set. I have x alpha thetas. Let me just tell you what these objects are. Because we need this g alpha theta which relates these objects. Let me take this two open set U1 and open set U2. We take two point charges which intersect. So, what's the possibilities? First thing is that they are both away from the singular set, and on each u alpha, my x alpha theta was just x alpha x theta is x theta. Then they are of course related by the original function g alpha beta. Then this g alpha beta is theta is the same. It's now if suppose u alpha intersects with this set, So one of the components does hit our set, and d beta does not. Then look at x alpha tilde. This is g alpha beta. Alpha tilde is dividing it by this. This was h alpha k times x alpha, and this is alpha beta or alpha k x beta, which is x beta. So in this case, g alpha beta tilde is original alpha beta divided by h alpha k. Now we need to see that this set is non-vanishing. It should be non-zero at each point. Although g alpha beta is does satisfy that condition, we just need to make sure that this happens as well. This is okay. This you can see from the fact that x alpha theta, look at x alpha theta. This set is a this is a holomorphic vector set, and its zero set is a co-dimension field. Because we have already started, we have defined these vector fields by reducing our singular set.
Yeah. The alpha beta is it defined also of the singular set? Like
They are also
the alpha beta is
defined on singular set.
and on the singular the alpha beta has vanished.
No,
Rank
no. G alpha betas are non-vanishing. Non-vanishing.
also on the singular set.
Yes.
In that case, the alpha beta by inch power k vanished.
Yeah. So that's what I'm saying. That's what I'm saying. So it needs to check that this should not vanish. And this does not vanish. You know, this can vanish. As you said, this is exactly what's defined. What defines this? What defines the singular set in R? But if you look at my condition, u beta does not intersect the singular set. So this singular set W it does not come in the intersection. So h alpha k is won't vanish in the intersection. H alpha k does vanish on some points in u alpha, but in the intersection of this h alpha k, this is y non-zero for all y in this u alpha intersection. From the intersection, it will be non-zero because this analytic set does not enter the intersection u alpha and beta. This is our okay. Let me give you a local picture of what this. So here is my analytic set W. Here is my u alpha, which intersects W, but my u beta is something over here. So on the intersection, this is not coming. So that's why H alpha is non-vanishing on this intersection. This is a non-vanishing.
What will be the coordinate at the singular
What?
while we are extending the map
Mhm.
exactly at the singular?
When you say singular, you mean
A singular
with respect to the foliation or singular of the analytics?
after removal is no longer singular, but
Correct.
it is singular.
Correct.
So at that particular point, when once you remove the singularity,
Mhm.
what will be G alpha beta for that corresponding point?
No, but that is not even there in his G alpha beta. I mean, that's not even there in his U alpha intersection
Yeah.
U beta, right? His U alpha intersection U beta is away from the singular set.
I mean, it's the next case.
He's not considered that
So
case.
yeah, it's the next case where that can happen. So
We haven't reached there yet.
yeah, so there will be three cases. Either both of them are away from the singular set, either one of them is like intersecting the singular set, and or either they both intersect the singular set, and then singular set can enter the intersection.
So if we could have a n minus one dimensional singularity, then we could not select a region which doesn't contain this singularity.
Sorry, if we have a
If let's say okay, the similarity dimension would be n minus 1. Then we could not select this uj region which doesn't contain no similarity.
Why?
So actually, the word singularity is already very, it is not a big singularity as well.
Okay, so look, we have a foliation and we have a corresponding singular set of this foliation, which is analytic set. Now, analytic set themselves have singular points. So, which singular points are you talking about? Yeah, because there should be like distinction. You should be clear that there are two kinds of singularities. And what we are doing is we are claiming that every regular point of this analytic set, which we are calling as a singular set of foliation, is a removable singular point of the foliation. Now comes the third case, where phi u beta. So now both of them intersect this singular set, and what happens is here it was defined by h alpha, and let's say here it's defined by h beta on the u alpha and u beta. So now consider. So what we have this. We have the original relation with the original vector fields and original mappings g alpha beta. What is x alpha tilde on u? This is h alpha to the power k1 times new vector field x alpha tilde, and in this case we have g alpha beta times h beta k2 x beta tilde. This is how we constructed x alpha and x beta if the neighborhoods kind of intersect in this singular set. So from this, what we get is x alpha tilde we said okay, let me write it first, then I might be able to explain. K2 h alpha k1 times x beta tilde. We get this identity. Now it's as you said, these functions. What I'm claiming is this one. In this case, g alpha beta tilde is g alpha beta h beta k2 over h alpha k1. Now here on the intersection where this g alpha beta tilde is defined, these two functions can vanish, and of course they will both vanish because it's the common defining set for this function on the intersection. But why would this still be non-vanishing on set? Yeah, why would that be? Well, yes, that's one thing. This is you can say, so this is a holomorphic set outside some set, right? So you take the zero set or the indeterminate set or the polar set, whatever we have, this dimension one set. Outside this set, this is holomorphic, this object. Now, if you look at these two vector fields, if you just look at this vector field, x alpha tilde, what's the zero set of this vector field? This is a codimension 2. Now, okay, not even codimension 2, since we are working with local case. We are assuming that it does not intersect any other set, so it's a non-vanishing in this case, because we are right now working with the regular part of the singular set. So even if you say codimension 2 set, it tells you that the zero set of this object, it would be at most codimension 2. Right? And same thing if you take this on the other side. So that it says that the kind of pole will also be set of pole will also be of codimension 2. And we can always extend by Hartog's theorem to codimension to set. So we get what? Yes. So you look at this equation. So the zero set of this object, this will be at most codimension 2. This is by definition. This is how we constructed these new vector fields. There are no, the singular set of these new vector fields does not have a codimension 1 components. If you look at yeah, here. So I remove the codimension 2 component, and the next, this remaining part, this will have zero set codimension. So this has the zero set of this vector field is codimension. So that's why we can extend these functions to whole of u alpha intersection u beta, and a holomorphic function on some open set. So what happens is this g alpha beta tilde now is holomorphic on u alpha intersection u beta, but it is non-vanishing away from the zero set. So what the zero set of this function is at most codimension 2. That cannot happen, right? Either this that yeah. Yeah, so I said I'm saying a bigger kind of statement. If I could just work with this, if I'm working in the regular part, yes, I can just say this does not vanish. This is non-vanishing. For this, no, because I'm on regular part. If we are taking coordinate chart in the look, so if suppose this is the singular set of my foliation that I started with. So if I look at these components, these regular parts, there I can make my new vector field to be non-vanishing. But if I'm starting with somewhere over there,
You are not here.
yeah, I'm kind of over here.
You are here.
Yeah, I'm kind of over here, but I was just saying something from there, which is weaker, which is still holds. So I'm saying even if you go there, these things will kind of help. These things will still follow, because even there the set of points. Yes, we are getting there.
So there is, it doesn't matter.
Yeah, it does not. Okay, yeah. So just assume that there is not many steps. Directly we have this. Okay. Well, that's the basic idea. I'm not writing everything, but that's the basic idea of how you get these new objects, how you get this saturated kind of new objects where you can, where you have the dimension, this condition of the dimension of the singular set. Now, we have not proved it, we have reached a contradiction kind of, you can say, because we were started with the saturated foliation. See, we have showed that there are further removable singular points. So if we start with a saturated singular holomorphic foliation, its singular set is very small. It's four dimensions at least 2. And now, what happened? What we have proved now, we have proved this. We have a singular foliation according to our definition, and we have saturated foliation corresponding to that, a unique saturated foliation. So I'll now kind of start forgetting about the original foliation, because I'll only be talking about saturated foliation. So given a saturated foliation, from the data, what we get is we get an analytic set analytic set V, which we are in this case the singular set of dimension greater than 2. We get an analytic set, a small analytic set in the manifold, and a holomorphic foliation on M minus V. So this is what we got. So if we have a saturated foliation, this is what we are saying. There is an analytic set of codimension at least 2, and outside this set we have a regular holomorphic foliation which does not have singularities. This is what we have. This is the kind of we have proved, but this is what we see from the what we have proved by reducing the dimension of single set. Now the interesting part is that we can go back. These two are not the same thing at this moment. If you go by the definition, if I'm giving you something or something like this,
So giving us an arbitrary analytic set of codimension 2.
Yes.
And saying that off of that you can always get a foliation.
no. So I'm saying you take any analytic set V, V, and if there is a holomorphic foliation given to you outside this V, then we have a similar holomorphic foliation on the whole manifold. Why is that thing?
It
Is
sort of
because
extends as a singular past V. I mean, you already have takeoff of V, right? The only place where it doesn't currently exist is on V.
yes, so away from V, it's nice. There are no singularities. I'm saying it will always extend as a singular foliation with this definition.
Okay.
It could possibly have singularities.
Could it become removed? I mean, would this be the saturated? Would it be a saturated?
I mean, I'm saying that these points could be removable,
Yeah. Okay.
or it could be non removable.
Yeah.
All I'm claiming is singular foliation.
Sure.
Since this is codimension 2, the saturated foliation could be big or small.
You are saying it is a zero set of the vector field which defines the foliation.
No. If I'm just giving you a holomorphic foliation in this complement, I'm only giving you data away from this singular set. I have a open cover of M minus V, union of UIs. This is M minus V.
But I think what he's saying is correct, that when you say that there exists a singular foliation, you're producing a foliation whose zero set is exactly.
So I'll be producing vector fields locally near points of this set, which kinds of gives you data like this.
So zero set will be V, right? Yeah.
So I think that is similar actually as slightly different. So
Yes.
there you say that you started in this certain foliation, right?
Yes.
The codimension is codimension of the singular set is greater than 2. You modified the like some data, right?
Yes.
So your definition foliation means set of data.
Yes.
UI, XI, and GI. But in the proof, at the end of the proof, you basically modify the data.
Yes.
You obtain a new foliation, right?
Yeah.
So you are saying that you have another foliation whose singular set is less codimension greater than 2.
No, I mean this extended foliation, this new data will give the same foliation. I mean,
So when you
if
say
it is
the
not
foliations, no, that is the question. When you say the foliations are same according to this definition.
okay, from this, so from this we have, as I said, if you go with this definition, there is a singular part of foliation and there is a regular part of foliation. If you say these two foliations are equal, then if you say two foliations, not equal.
No, I think, okay, there is something weird about this because he's assuming it's saturated. So the points that he removed shouldn't have been there because it's saturated. So I think it's a sort of proof by contradiction.
Yeah.
Like
I
suppose
mentioned
there
this
is
thing.
this n minus 1 dimensional point, then he shows you that you can get rid of it, which means it didn't exist in the first place because it was a saturated.
Yeah, okay, you have a new set of data.
No, that the new set of data is sort of contradiction.
So maybe this thing will be clear when I prove identity theorem for this foliation.
There should be some definition when foliations are same. I can go by this definition.
Well, when we know what this means for holomorphic foliations, that just means all the leaves are Same means
Geometrically, you get the same.
But the thing is, they won't be the same because removing the singularities will get a different foliation. Just that one of them has the singularities removed.
Right. This theorem, should you say that there is another position?
No, I think here he's saying that this
no,
cannot be done.
I'm just extending my original foliation.
It was extending the original foliation, which
some
is a
singular-
contradiction because it's not
Oh,
supposed to be
you're
possible.
putting more data.
Yes. So I'm putting like, okay, these data are defined on M, but these singular set of these vector fields, they could be codimension one set. I'm kind of extending, I'm kind of giving you new data, but when I'm giving you this new data, locally you can see that this vector field xi, x alpha and x alpha tilde outside some set, outside this singular set, they're giving you the same solution. Because on the set that this function is not vanishing, does not vanish. You have two vector fields which are related by a non-zero, non-vanishing. They give you the same solution, same direction than the vectors.
I guess his point is that if somebody gave you a saturated foliation, would you have to then further modify it?
No.
It's
It's a
already
proof
best.
by contradiction, as I said.
So somebody gives you saturated foliation, you don't have to do anything more. You can just take it Z, yeah?
But here it's something different. I'm done proving this. Like I'm saying, there I proved that if you start with a saturated singular holomorphic foliation, then its singular set is small, of codimension at least 2. Now, if you have this saturated foliation, now you know the singularity condition from there. But this is giving us a codimension 2 analytic set, which is the singular set, and it's saying that there is a foliation, holomorphic foliation in the complement of this analytic set. We just take we can just take the data from here. It's the converse part which is more non-trivial. Just saying that we have a holomorphic foliation outside some 4-dimensional analytic 2 set. This will extend to a singular holomorphic foliation on whole of M. When I'm saying there exists a singular holomorphic foliation, what I'm saying there exists data on all of manifold. So what I have to do further on, I will be proving some coordinate charts near points of the singular set, and I will have to define vector fields which defines the singular foliation. I mean, outside we know. Okay, before I go to this converse part, let me prove this identity theorem for singular holomorphic foliation, which we saw it for non-singular holomorphic foliation. Let me prove it for singular one because I'll need it for this. Yeah.
Just sorry to bother you.
Yeah, no.
So in this definition, do you have some kind of maximality? This property
Actually, this data should be maximum.
maximum. Right?
Maximum.
Now I am completely.
Whenever I'm writing this data, I'm always assuming this is a maximal collection of such.
For the last question you posed, couldn't you just take limits of vector fields?
So it's in the sense.
Like if you have a foliation
They could
outside
be
a
going,
codimension
they could be
set.
going up and they should be going to zero. I don't, it's
But they don't
codimension
have
2.
to, like, it doesn't have to end up being singular on that set.
Yeah, that's what I'm saying.
It's good or it might not.
But priori, you don't know whether the limits can be taken account, right?
Right. I mean, if it was loose foliation, you wouldn't be able to do it.
No, but for each point, you need to just you have to essentially remove. You do like a hot off. Yeah. Right.
That's what we do.
Yeah.
Identity principle for is that let a complex manifold two I'm taking saturated position to singular such that same as F2 on some open set P set in we know that they are same on some open set, then so of course I'm assuming my manifold will be connected as a piece. First step would be same as we did for the identity principle for non-singular foliation. What we kind of do is we start with the maximal kind of open set on which they are same. That will be maximal domain containing maximal connected domain containing V such that this F1 and will show that if this set is not equal to the whole manifold, then we work on the boundary points of this set and we find another neighborhood near that point on which they are same and we get a bigger set contradicting this definition. But note that if this is W, so suppose we have some non-singular point in this boundary of this open set W. If there exists P in W such that this P is not a single set of F1 and F2. So we have two singular sets corresponding to each foliation. If there is a point in the boundary which is not in the singular set of any of these two, then we can just from previous the argument I gave from previous time. What? Foliation? Yes. So yes. So last time I proved identity theorem for k-dimensional foliation without singularities. This one I am just proving for one-dimensional singular holomorphic foliation. So if this point P is regular for both singularities, both foliations, then there exists chart for each of these foliation in which our leaves look like annual complex disc. And on some intersection, they kind of overlap. Because on this, the leaves are same, the foliations are same. So we'll get the same thing that if we take the transition map from one open set to another, this last n minus k coordinates, or since we have defined our foliation in terms of vector fit, we start with a vector fit del by del z over here, and if you push forward this vector fit in this open set, it will be again some non-vanishing holomorphic function times del by del z. Is the argument clear? What I am trying to say. You consider I have foliation is given by del z1 here on u1, and I have this another open set corresponding to foliation. This is corresponding to F2 and this is F1, and here is my point P. Again, this is given by del z1 and this is given by del z1 in their respective coordinates, of course. But if we take the transition map from here to there, we know that on some open set these leaves kind of the leaves are same. If you take this neighborhood to transition maps, first over here, you consider it on the plane of the other location. Since the leaves are same, the map will be 0. So it will take these objects to these objects. Then we can use identity theorem for this, so that they will be. So if this is the intersection part of Q and there will be the position would be same on the overlap, on the whole overlap. So that gives us that. So if you take this is the intersection of these two sets. To prove that the foliation is same for foliation same on this set, and we attach this set to the W to get a bigger set. It's the case that if this point P is a singular point, so that's reduced our case because each singular set is a 4-dimension 2. So we are kind of already in the case that W is very big. The complement of W could be on the 4-dimension 2 set. Okay, so if P is a singular, then we are able to this argument that I will give, it might or it might not give contain this case, but if P work with P, what happens is suffices to prove the following. Suffices to prove the following. Component is and x y denote define f1 and f2 on u and f2 on u, and the 0 set four-dimensional condition is 2 So if x and y define the same foliation on some node entry open set with data in U, then this F1 and F2 are same for. But I converted this problem to local one. How it suffices to prove this? What we are doing is we are taking one open set near this point, even if it is singular, even if it's not. By definition, we get two different vector fields or two vector fields defining each foliation on this open set. And I'm saying that on this open set, we have two different vector fields. So 0 set is 4-dimension 2, and they are giving you the same foliation on some open set. The some open set is the intersection in the W. If they are giving us the same foliation in there, so they will give us the same foliation on the whole. That is, we get a neighborhood over here. So if you prove this, then we get a contradiction in the sense of maximality of W. This is what we will prove. Okay. So right, the vector field x, the components xi by then xi and y as then y to xi holding us. Right, vector fields in local coordinates. Not local coordinates. We are working in CN, so we have the coordinates. Know the coordinates. Okay. So the foliations are same on some non-empty open set B tilde, and the singular set of these two vector fields is a codimension too. So there exists, we can just assume that this B tilde or there is an open set B tilde on which the foliations are non-singular and they are same. So on let's say on B tilde minus the zero set of these two vector fields. So this is the open set because this set is very small. This is the codimension 2 set. So this is the open set. On this set, I claim that my vector fields satisfies this solution. I'm claiming this is true. Where P is a, let's call this is a B and this is B tilde. If point P belongs to this set, then the both vector fields are defining the same position, so they are kind of pointing in the same direction. So these two vectors will have some number, so they are related by some scalar. This is the scalar, and it depends on the point P. Is it clear why this is true on this set? Because both vector fields are non-vanishing on this set, and so they give you in the since the foliations are same on this set, the direction they correspond to is the same. It's just that they could be scalar multiple of each other. So if we have this foliation, the corresponding vector field which defines it, the vector could be this, or it could be this. As I said, I don't care about the speed. All I care about is the direction, which is saying that the distribution is the same. So since I'm in one-dimensional position, I have one-dimensional distribution, which is one-dimensional subspace at each point, one-dimensional subspace of tangent space. So two vectors in one-dimensional space, they are related by a scalar.
Is singular point?
What?
Is a regular.
These are regular.
Okay.
I'm removing the singular points. Now, yes. And lambda is in actually star of A tilde. From this we get this. This is because from this equation what we get is xi of p is same as lambda p of yi of p. Xi and yi are these functions. So this is like there are two vector fields on each side. These are holomorphic maps. These are components. If two vector fields are created, each component is created by a scalar. Now, on the set where these two vector fields are non-zero, xi and yi are non-zero, this lambda p is xi over yi. So it is holomorphic on some set. It is holomorphic, and lambda is holomorphic on the set where p tilde minus yi equal to 0. These are holomorphic functions. So on the set where this yi does not vanish, this is a holomorphic function. a ratio of two holomorphic functions. But if you take a point P in V tilde, if P is in V tilde, there exists I such that this yi is non-zero. Because the vector field y is non-zero, there must be at least one component which is non-zero. So from there we can say that from these two properties we get that this lambda is non-vanishing on V tilde. And since the vector fields are defining the foliations on U on our manifold U in CM, these sets these sets this I or yi. These functions are well defined on U minus y equal to 0. The xi and yi by definition are these vector fields are defined on U. So where this component yi is non-zero, we have this ratio of holomorphic function will be holomorphic away from the zero side of y.
Sir, you showed that lambda is holomorphic on V tilde minus yi equals 0. Why does that imply it's holomorphic on V tilde?
Because for each point P in V tilde, there exists one such I.
Right.
And the lambda is same. We can change I.
Yeah.
So here's my picture. Here is V tilde and here is U. On V tilde, I showed that these two vector fields are related by a non-vanishing holomorphic function. We want to show this on volume. But look at this set, U minus yi. This is something, yi equal to 0 is something like this. These functions are defined on much bigger set, not in V tilde only. And xi over yi, this is equal to lambda on V tilde. So we kind of have extension of lambda to a big set. You can define it in these functions. And where this extension is going to be, this will be on for f u minus the zero side. Yes. So in this set, lambda is this is what we get from this thing. Again, using the same idea. I extend my lambda to big domain to flags xi and yi, which are defined on whole of U minus some set. But if you take any point P in this set, at least one of the xi's and yi's will be non-zero. This is by definition that we are removing those points where vector field vanish. If a vector field is non-zero at a point, one of its components will be non-zero. So we take the corresponding xi by yi, and we get that this lambda map actually has an extension to this set, and it is holomorphic in this case. And by definition of this, this will be non-vanishing. Now, how big is this set? This is codimension 2. Now we again use the Hartogs extension theorem, where we say that we can extend our holomorphic function to analytic sets of codimension at higher than or equal to 2. So this gives us that lambda will be again also it will be non-vanishing as well. So we get a global non-vanishing holomorphic function which relates the two vector fields. This. There. So this was on V theta, but we showed that this actually holds on U, hold on U. They give us the same position on U, and then go back to our construction, and we prove that this W is actually the whole manifold. And the time is up. What I was trying, I wanted to prove, I couldn't. You want me to give you a statue? Yeah, that's what I'm saying. You want me to give you the idea of the proof in 5-6 minutes, or you want me? If the audience is interested, then I and the organizers are. I'll try to just give you the idea of this. And, and analytic set, 4 dimensions, and at least 2, and we have a holomorphic foliation f on this m minus p. Then there exists a singular holomorphic foliation, a unique singular holomorphic foliation. On M, such that this is f tilde, let's say, such that f tilde restricted to m minus p is. Now again, what we need to, so we have this analytic set P in the complex manifold M, and we are given this set of vector fields and open sets of the complement of the domain M minus B. What we want to do is we want to give the set of data on points of V as well. So we can convert this problem into a local one. The local in the sense, so we have a domain U or an open point in Cn.
Is B.
Yeah, so V could be the singular set, or the singular set could be contained in. There exists a unique foliation, saturated foliation. So we could start with a trivial foliation like this, and we started with the analytic set, something that says this point. When we said we can extend it to a singular foliation, the points of this analytic set could be removable.
Started the police everywhere. They just forgot that you had it.
Yeah, so suppose we have this U in Cn, and we have this analytic variety P in our case. This is and we have foliation F on M minus P. So we want to get a vector field on points P in this analytic set. So to do that, instead of writing, let me just see the kind of idea that I want to. So on M minus B, I have these open sets, which is a cover of M minus B, and on each ui, I have a vector field xi. Now I can write, since it is in Cn, I can write my vector field xi as not x, let's say x alpha as x alpha 1, then by x alpha I, then by del xi in the coordinates. And by definition, since the analytic set, since this vector fields does not vanish, since this vector field does not vanish, I can assume that there exists. I can assume that x alpha n, this is non-zero. This is non-zero on u alpha for each alpha. So this I can assume. Since V is codimension 2, U minus V is a connected set, and on the intersection, these vector fields are related by this. I can assume that there is one component x alpha n, which is a non-zero function for each alpha. And basically, this is what we use to get the vector field. Consider these maps f alpha is x f alpha j. This is x alpha j over x alpha n. So on each open set ui, on each of these open set ui, I consider these maps. Now these are meromorphic maps, of course, because these can be zeros. These are just non-vanishing. These are non-zero, but they could vanish at some points. So it's a meromorphic functions. These are meromorphic functions, but they satisfy this property. F alpha j restricted to u alpha intersection u beta is to f alpha f beta j this is using this. If you look at x alpha j is same as g alpha beta x beta j, and x alpha n is again g alpha beta x beta n. So you divide both sides, you get the equality. Of course, where they are defined, so they are equal as a meromorphic function. And then, so the idea would be, to, since we have this local data, these are meromorphic maps on open sets, and on intersection they overlap. On the intersection they are same. We use Cartan's theorem or this cousin problem kind of thing. Oh, yeah. I said cousin. Oh, you said cousin. Okay. It spells the same, right? Using the seek theory, right? Yeah. Yes. So what we get is one function, one global function on one meromorphic function on which we can write as g by gj by hj. This is on u. So what we had from there, we had a meromorphic function on u minus b. Meromorphic in the sense locally they are represented through this form. And this set of data using this Poisson's problem, we can get that on u itself we can find two holomorphic functions such that this meromorphic function is a ratio of these two holomorphic functions, and the zeros is a condition of the common zero set of these two functions, which is codimension.
X alpha n can be identically zero, right?
No. That's why I started with. I said that we can start without closure generator. Can assume that at least one of the components of each vector field, the same component, is non-zero. And so, yeah. So getting this vector field, getting this meromorphic function on U, we define something like this H to be H1, Hn minus 1. So we have these maps for J from 1 to n minus 1. For each component x alpha 1, x alpha 2, x alpha, the denominator is x alpha n. We have this n minus 1 meromorphic functions on U. We take these denominators, we have this, and somehow I'll skip the calculation. The vector field that we get is something h del by del xn plus so this is gj by hj times h del by del xj. This is summation over say from 1 to n minus 1. So this is a candidate of the vector field which defines, which extends this position.
This minus the analytic set, right?
Yeah. Now, but this is a holomorphic vector. Look, this is a holomorphic function. This is just product of these functions h1, h2, hn minus 1. Now, this is meromorphic, yes, but we are multiplying with h. What is h? H is the product of this.
Like coming here, H1 is
So h1, h2 are coming from this. Fj is gj by hj. So for the j component, we have gj by hj, but hj will cancel out the hj in h. So this is a holomorphic vector. And what we can check that outside this analytic set, outside the zero set or something, these vectors correspond to the direction of the original foliation, the holomorphic foliation that we started with. So this does extends, kind of extending our original foliation on the analytic set, which could be similar because this vector field could have zero set. We can just remove by a process the n minus 1 dimensional components. So we can get a saturated foliation, singular foliation on whole manifold by constructing like objects, vector fields like this on the analytics. The calculation are not there. I was just trying to give you the idea of how this is going. I want to say, and of course we will have to use the identity principle at the end to say something that since the original foliation and this foliation are same on some open set, on the whole open set they are in the same foliation. By the way, yes, before I finish, this result, which is the converse of our first result, this is interesting in another sense. So I just said the Hartog's extension theorem, which says that any holomorphic function or any meromorphic function on an open set minus some codimension, at least two analytic set, will extend to a holomorphic and respective meromorphic function. Now, holomorphic foliation does not have this property. If I have a holomorphic foliation in the complement of an analytic set of codimension 2, it won't extend to a holomorphic foliation, although it does extend to a singular holomorphic foliation. So just in this result, we can, instead of starting with a holomorphic foliation outside an analytic set, we can start with a singular holomorphic foliation outside the analytic set. And the same kind of proof will give you that a singular holomorphic foliation always extends on codimension 2 analytic sets. So this is something similar to Hartog's extension theorem, the statement at least, like this. So from now on, or maybe when I give my conference talk, I won't give the definition of foliation in terms of vector fields. Because of this, I can just say that a singular holomorphic foliation is just a regular foliation outside some analytic to analytic dimension, codimension to analytic set. Well, I already took 15 minutes instead of 7, so I'll finish it.
This was Sahil's lecture, so thank you, Sahil. Thank you.